Welcome everyone to our talk here in October for the 2DCC. Today we have Dr. Eric Hudson from Penn State University. He's an associate professor in the Department of Physics. He is also the associate head for diversity and equity in physics, or the College of in Physics. Okay. Eric is also the director for education, outreach, and diversity for the 2DCC. He'll be giving a talk today on AFM and STM. Eric?
Thank you. So, on behalf of the 2DCC, welcome. What I'm going to be telling you today is about atomic force and scanning tunneling microscopy. And this is in some ways a follow-up of a very nice talk that Josh Robinson gave almost exactly a year ago on atomic scale characterization of a variety of materials using techniques that we have available in the materials characterization lab. So I'm basically narrowing in the focus on AFM and STM, and I'm going to be presenting in somewhat of a tutorial style. So please, if you have any questions along the way, feel free to just yell them out at me, and I will try to answer them rather than holding them until the very end, in which case I forgot what I was talking about when you had the question. So before I get into the meat of it, I just want to remind those of you who maybe aren't familiar with the with the 2DCC, what is the 2DCC? So we're a materials innovation platform, which is an NSF user facility, and we focus on three different techniques. One is the growth and characterization of thin films. One is bulk crystal growth, and then theory and simulation. And of course, what I'm going to be talking today falls into the in situ characterization. There is one instrument that we have which has an STM built into it, and that's our MBE system, which is over in the basement of Davie. It is actually currently being installed. And the part I'll focus on here is the cryogenic LT nanoprobe, which is a 4-tip STM and SEM combination. So it's connected to the MBE chamber, and the idea is we'll be able to grow materials and transfer them over into the STM and make measurements immediately after growth. This is not the only STM that's available in the 2DCC, though. As I mentioned, we have a close collaboration with the Materials Characterization Lab, and they have two Bruker icons available, one of which has a heating and cooling stage, so there's a wide variety of temperature ranges that you can make measurements on. If you're interested in using that, you can contact Tim Teague. And then my group has a what we call the Scanning Nanoscale Interface Probe Ensemble, or SNIPE, and this just recently came online for doing UHV, AFM, and STM measurements with sample preparation and optical axis, and I'll show you a little bit later in the talk why that optical axis is a useful thing. And we are also part of the 2DCC, so although you can't go in and just put your sample into it, I'm very happy to collaborate with people in making measurements of their materials. Okay, so for this talk, what I'm going to talk about is what can you do with these types of instruments. I'll start with a very broad introduction to scanning probe microscopy, and then focus on some specific techniques in STM and AFM with some examples along the way. Okay, so introduction to SPM. This, I think, summarizes nicely what SPM is, which is it's a technique for imaging, which means spatially resolving materials at down to sub-nanometer length scales using a probe which is scanned over the surface. And so let's sort of break this into parts. First of all, there's the scanning part, and for scanning technology, we use a piezo scanner, typically tube scanners, at least in the instruments that I've mentioned so far. These are piezoelectrics. They convert voltages into displacements. The scan motion is typically about 10 to 100 nanometers per volt in the XY range, and about 1 to 10 angstroms per volt in the Z range. And what that translates into total throw, when you put a few hundred volts on this, is you get about 1 to 10 microns of throw in XY, and about 10 to 100 nanometers throw in Z. And of course, this depends on the scanner and on the voltage that you end up applying. But what you end up getting then is very high precision, so on the order of 2 picometers in X and Y and about 20 femtometers in Z, at least for our system. which means that you're able to make very precise measurements of position in these systems. So that's scanning. What you're scanning over is a surface, and so here's some systems, some general scanning probe instrument, and the key is you need to have some feedback mechanism so that you actually hold the probe at some constant height, for example, relative to the surface that you're scanning over. And if you're going to do that, you need to have something which is sensitive to atomic scale changes in the displacement. You actually want to measure the individual atoms. So how do you do that? Well, there are a variety of them. I'm going to focus on two right now. One is tunneling current, which is what's used in STMs. And so the idea is in an STM, you have some tip, which is just a piece of wire, some metal, and some sample that you want to study. They're separated by some distance d, and they each have some work function associated with them. And what happens is that you get tunneling from, for example, in this case, the tip into the sample. And the current that flows between the two has this decay constant kappa, which is on the order of an angstrom. And that's what gives STMs their ability to make very precise measurements in Z, because if you change the distance between the tip and sample by the order of an angstrom, you change the currents on the order of, well, 1 over E. So it's a big change in the current. It's very easy to see changes of about 1/3 in current, so it's very easy to see changes in height of an angstrom. And in fact, we can make measurements down to sub-picometer levels with an STM. In an AFM, or any sort of force microscopy technique, a common way of doing the feedback is by using cantilever deflection. So you have a cantilever which has the tip on the end of it, and this cantilever is floppy. You bounce a light off the end of it, and you pick it up on, in this picture, it's a quad sensor. So as the cantilever goes up and down, the light deflection goes up and down as it goes to the side or tilts. That moves the beam left and right, and then you just make a measurement of how much light is falling on the 4 parts of the sensor, and then that tells you what the displacement of the cantilever is. There are, of course, other techniques, and I'll mention them a little bit later, fabric interferometers, piezoelectrics, and so on and so forth. Okay, so that's how we scan and measure the scanning as we move over the surface. There are a wide variety of SPM techniques. This is by no means exhaustive. There are a lot of force-based probes, so atomic force, lateral force, chemical force, Kelvin probe force, magnetic resonance force. All of these at their heart, though, are force microscopy techniques. So the idea is you basically change what the interaction is that's leading to the force, but then you're just using a normal force probe and measuring what the displacement is and translating that into a measurement of force. There are also non-force-based techniques. The one I'm going to focus on is STM, tunneling microscopy, but there's also optical techniques, so SNOM or NSOM, scanning capacitance, squid, thermal gate, and so on and so forth. So lots of different things that you can measure with scanning probe microscopes. And if you have interest in any of these, although sort of the headline of what's available in the 2DCC is atomic force and STM, certainly once you have atomic force, you can pretty much easily do any of these. Well, this last one's a little challenging. I'll talk about that a little later, but the other one's pretty straightforward extension to a standard AFM. If you want to do scanning squid or NSOM, that would take a little bit of upgrade to the instruments. Okay, so let's turn now to STM and the details of what happens in an STM. So one of the things that the STM is good at is doing atomic scale imaging. Basically, it's a high-resolution microscope which enables you to zoom in and park your tip over individual atoms and study them for long periods of time. Which, if it's just one atom out of 10 to the 23rd, it's not particularly interesting. But if that one atom happens to be an impurity or something, and you're trying to understand how that influences the material properties around it, it can sort of warrant the attention of being parked over for a while. One thing you'll notice about this, though, is that what you're looking at here is a bunch of selenium atoms in niobium diselenide, which is a low-temperature superconductor. And we know that the selenium atoms are all essentially the same, but if you look at it here, you'll see that it looks like every third selenium atom is sort of higher than its neighbors. And the reason for that is that STM doesn't really measure atoms. What it measures is electrons. Now, electrons tend to hang out around atoms, which means that if you're looking at the electrons, you often see the atoms. But you also see electronic properties. So here, for example, we have a charge density wave. The electrons are reducing the energy of the system by going into 3 waves. One wave front going that way, one wave front going this way, one wave front going that way. That interference of those 3 wave fronts makes the pattern that you see here that leads to every third atom looking higher than its neighbors. And you can see in the trace below. So that is important to keep in mind that when you're doing STM, what you're really looking at is the electrons. And as you change the energy that you're looking at, you're going to see different sets of electrons, and hence your topography and what you're measuring can definitely change. Here's a good example of where that electronic wave behavior dominates. So this is the surface of copper 111, and you no longer see the atoms or anything that you would associate with atoms. Instead, what you see is the electrons looking like water in a swimming pool. Here's a step edge. This is a single atomic height. There's 3 atomic steps here. And what you notice is the electron waves wash up against the step edge and reflect backwards, leading to a standing wave. That's a carbon monoxide molecule, and it looks like someone's tossed a rock into a pond, right? You see the electrons, which are reflecting off of that and forming standing waves around it. So that's topography. What really gives the STM its power is that it can do spectroscopy. So to think about spectroscopy, let me just sort of go back to the picture of the density of states of the sample that you're trying to study and the density of states of the tip. Now, we try to pick tips which are very boring, which really have these sort of rectangular, of course this is a cartoon, but basically not any interesting features in the density of states. And when you bring them up against each other, their Fermi energies equilibrate and nothing happens. But if you apply a voltage, here I applied a positive sample bias, which shifts that energy down relative to the Fermi energy of the tip. Then you can get a current flowing. In this case, we have electrons flowing from the tip into the empty states of the sample. And if you integrate the density of states from the Fermi energy up to the energy that you've shifted the bias by, that gives you a measure of the current. So the current then is a measure of the integral of the density of states. The integral of the density of states is okay, but what you really want to measure usually is the density of states itself. And the convenient thing for that is if you look here, if I shift the Fermi energy now, if I apply a small dV to my bias, I'm going to get a small change in current, and that change in current is proportional to the local density of states. So when we do STM, we often do differential conductance measurements. That's di dV. And when we do that, we pretend that we're essentially looking at the local density of states of the material, which to first order is a decent approximation. Okay, so with this ability to do scanning and to do energy variation, we have access to a sort of the whole volume of the local density of states information. So if you imagine this is local density of states as a function of x, y, and energy, we can do topography, which is basically measuring an integral of the density of states as a function of x and y. We can park the tip at one location, let's say here, and just change the energy and measure the differential conductance, and that gives us these conductance spectrums, which are, again, density of states as a function of energy. We can scan along a line and take a number of spectra and get line cuts, which enable you to see how do features change as you go through impurities and stuff like that. Or we can sit at a single energy and map out how the density of states varies spatially at that energy. And that gives us something called a density of states maps, which gives you a nice image of, for example, this is an individual zinc impurity in bisco, which is a high temperature superconductor. And you can see how the electrons at that energy respond to the presence of the impurity. To turn to materials which are studied in the 2DCC, here's graphene. This is pristine graphene. And then we have boron nitride doped graphene from the Tronis group. And you can see individual nitrogen impurities, which make these triangular patterns around them in the density of states. And here are two individual impurities, which make these sort of rose-shaped impurity patterns, and we're actually in the process of investigating these now and trying to figure out what, we don't actually know what these impurities are. From previous investigations, we believe this is nitrogen. Perhaps we're actually getting boron nitride into the lattice at this point, which is the goal of the investigation. Here's another material. This is in collaboration with Penn Samar's group. So this is 83 nanometer thick chromium doped bismuth telluride, and it's sitting on an insulating substrate. So this actually provides a challenge to STM, because STM, of course, needs conduction in order to work. And so if you're on an insulating substrate, you have to actually make contact to the film, which is on top. And the way we do that is fairly straightforward. We just paint conducting epoxy up over the edge of the sample onto, so it's connecting the top surface to the sample holder. The issue, however, is if you then need to go and cleave your sample, how do you do that without cleaving off the conducting epoxy, which is actually allowing you to make contact to the material, electrical contact to the material? And then how do you actually find the location on the sample where you haven't completely cleaved off this 80 nanometer thick film? So what we're able to do in InSite, one of the powers of it is that we have optical axis, so we can actually place our tip very precisely over features that we want to study. And so we were able to put the posts that we use for cleaving this material. We basically used an extension of the Scotch tape method. We put some epoxy on a post, glue it onto the sample, and knock it off, and then that peels. As it's being knocked off, it peels off the top several layers of the film, leaving you a nice flat atomic surface to measure. So we put that post very close to the edge of the sample and made the contact on the other side, so that when we peeled off that post, we left the electrical contact. Then we just need to go and place the tip right close to the edge of the sample, so that we were far away from any regions that's damaged from the post going off, and any region from where the conducting epoxy is making a mess on the top surface of the material. And with that, we're able to get atomic resolution. These are individual chromium dopants in this bismuth telluride film, and we're beginning to investigate that. So not only do you have real space information about materials, though, you can also get k-space information via STM. So a picture showing how you do that is from this sort of very nice visualization. It's called Amber Waves by Don Eigler, who was sort of one of the pioneers of STM at IBM. This is again in copper 111. And if we zoom in on the step edge here, you again see those waves reflecting off of the step edge, as I showed earlier. And what that comes from is you have some incoming k vector, you have some outgoing k vector, and the wave vector that you get out is just the difference of the incoming and the outgoing. And then that's 2 pi over that wavelength that you end up observing in the image. So the question is, can you get dispersion information, so the energy dependence of this, from images like this? And the answer is yes. If you measure the differential conductance for fixed energy as a function of position, and then you change the energies, you can find out at each energy what the wave vector is. And so an example of this is done by Pascal's group. Here's the real space as a function of energy and as a function of displacement from the step edge. What's the density of states? And if you take the Fourier transform of that Fourier transform tells you what the differential conductance is at a fixed Q. In this case, it's Q is equal to 2 times Ky, and the energy. So why is it 2 Ky? Well, if you think about what's going on, let's look at some contours of constant energy of these surface states that we're tunneling into. In silver, which is what Pascal was studying, they're fairly boring, they're basically circular. And so if I look at just one of those, so I fix my energy, I look at one contour constant energy, think the Fermi energy, the Fermi surface, for example. So I'm looking at the Fermi surface, And every point on that Fermi surface, well, for this, the K associated with this direction, that's Ky there. The reason that we see it here is that it's scattering, though, between the incoming wave and the outgoing wave. So it's scattering between these 2 points. And those 2 points are separated by 2 Ky. So we can actually, from just measuring this wavelength, or taking the Fourier transform and measuring what Q is, we can map out points on the Fermi surface, or at any energy surface, depending on what energy we happen to set the STM to. And you can actually take this technique and extend it. When you have a step edge, you're really just looking at one dimension, which is the dimension perpendicular to the step edge. If you sprinkle impurities randomly through a material, then you get scattering in every direction, and you can actually sample the Fermi surface in all directions. And so we've mapped out, for example, the Fermi surface of high-temperature superconductors using this technique. You can map out other systems, topological insulators, for example. Vidya Madhavan's group has done this and looked at the absence of backscattering in topological insulators. So it's a really powerful technique for doing K-space investigations with a real space technique. Pausing dramatically for questions, but there don't appear to be any. So I will now shift gears to atomic force microscopy. It's going to be a real short talk, so someone has to start asking questions. So force microscopy is a force-based measurement. The idea is that some interaction between the tip and the sample leads to a force. You hope that that force doesn't destroy the sample, so you want to keep the force small, maybe under a nanonewton. But it needs to be big enough that we can actually measure it. So how do you do that? Here's a typical setup. You have a cantilever with a probe on the end of it. The thing you're measuring is underneath that tip. And you have an external displacement sensor, which as that cantilever bends due to interactions with the surface, the distance between it and the displacement sensor changes, and then you read that displacement and convert it to a measurement of force. Here was the very first way that Binnig, Quaid, and Gerber were thinking of doing this. They had an STM tip on the back of the cantilever and used the STM tip to measure the distance between the, or the deflection of the cantilever. I don't know who would have thought of doing this. I mean, STM on a flat surface, which is huge, is hard, on the back of the cantilever seems like a nightmare. Anyway, this is not how it is done now. There are a number of displacement sensors, all of which are much easier than that one. This is probably the most standard, using a laser beam deflection into a quad sensor, which is able then to measure deflection both like this and laterally. A Fabry Pro interferometer gives you enhanced signal when you reflect off the back of this, but you need to set up the distance between the end of the fiber, which is bringing down the light, and the cantilever fairly accurately, so it's sort of more complicated. Piezoelectric cantilevers take advantage of the inverse of the effect that we use for scanning in these systems. But all told, all of these typically end up with a noise floor that's on the order of a femtometer per root hertz, which, if you think about it, is pretty impressive that you're able to measure sort of nucleus sort of length scales if you wait for a second. So what is it that sets that sensitivity? Well, it's thermal noise. So there's motion of the cantilever, and that's driven by temperature. And then that leads to this sort of noise spectrum in nanometers per root hertz that depends on the stiffness of the cantilever and the temperature and the quality factor and the resonance frequency. And in terms of thinking about this, if you're used to thinking about Johnson noise, right, which you're wondering why does it go like the 1 over the square root of hertz, it's the same reason that Johnson noise does, except it's a mechanical resistance instead of an electrical resistance that you have in Johnson noise. So what does that mean practically? Well, if you have a rectangular cantilever, some length, some width, and some thickness, the minimum force that you can measure depends on the cantilever dimensions. It depends on the material properties, like the Young's modulus, and it depends on the thermal energy. And it depends on the bandwidth that you're willing to narrow your measurement down to. So to give an example of how good you can get with this, Dan Rugard's group has been working on MRFM, magnetic resonance force microscopy, and so they want to measure the impact of sort of single spins and single spin flips on the force between that spin buried in the material and the tip, the cantilever, which is above it. Which you imagine that's a very small force, and so they had to really perfect this technique. So what do you do to minimize this force? You use very thin to reduce T, very long cantilevers, which are not lossy. So Q is big, sorry. Can't do much with the Young's modulus and sort of these material properties independently of Q, but you can go to very low temperatures and low laser power. Yes?
Question online. Is the Fabry-Perot technique the same as TERS?
TERS. I have not done TERS, so does anyone in the room know the answer to this question?
That's tip enhanced Raman. I don't think so.
No, it's not that. No, it's not the same. So in Fabry-Perot, all you're doing, you're sending in a single wavelength. You're looking at the multiple reflections of that, which just enhances the interference pattern, which gives you a sort of a cleaner signal. That's good. So low temperatures, low laser power, because of course the laser bouncing off the back of the cantilever will warm up that cantilever. And what they were able to achieve was a minimum force of about 240 zeptonewtons. So that's 10 to the negative 21st newtons, which is just phenomenal that you can measure forces that small, and then they can actually do MRFM. But as far as I know, they're the only ones who can actually do this. So set your sight 1,000 times higher than this, and you'll be totally fine. Okay, so as I mentioned, there are a wide variety of force microscopy-based techniques. So I'm going to mention several ways of doing force microscopy. So one is contact AFM, and this is sort of the simplest way of doing AFM. Basically, you take your cantilever, you slam it into the surface, and you just drag it over the surface. And then you make a slight upgrade to that, is that when you slam it in until it deflects to a certain amount. And as you drag it over the surface, if you notice it deflecting more or less than that, you adjust the height to make the deflection be the same. And that constant deflection you can then read as constant force. The problem, of course, is that you're dragging a tip across your surface and making all these channels in it as you're doing that. And so it's not great for soft surfaces because it can really damage the surface. One question you might ask, though, is what does contact mean when you're looking at the atomic length scale? So here's a typical force distance curve. So you have this long-range van der Waals attraction typically curve, which tends to suck the tip into the surface. All right, so the force here is negative, it's attracting the tip. And then you have these repulsive forces, the short-range Coulomb interaction, which turns on when you get really close to the surface, and that drives the force positive, repelling the tip away. So if you really try to push your tip down into the surface, the cantilever is going to bend upwards away from it. So when we say contact, what we're talking about is that place where you're in these short-range repulsive forces. Now you can measure a force distance curve like this. You can just sweep z back and forth, and you can measure what the deflection is as you do that. And here's an example of doing that. So as you sweep in from large distances, you're gradually moving the cantilever towards the surface along this red curve. At some point, it jumps downwards. Okay, so that's this attractive mode. It's getting sucked into the surface. And then as you go in closer and closer, it begins to become repulsive. So that's where you're actually making contact with the surface, and it's bending the tip away. And then once you get to a place where you figure you've done enough damage to the sample, you can reverse course and you can back out, and it will back out along the blue curve and go back. Now this is a particular kind of material situation, just to get in your mind what's going on. When you look at these force distance curves, this is approaching surface with some drop of water on the surface. So as you go in the water actually grabs onto the tip and pulls it in. And when you go back out, there's this different liftoff force, which is larger than the original force that was attracting you in, because you need to actually break contact with the water to pull the tip away from the surface. So when measuring force distance curves, there's sort of lots of things to think about of what's actually going on the surface of the material that you're looking at in order to lead to the effects that you see. I talked about working in contact mode and how it damages materials. Another way of acting is in non-contact mode. So you go away from the surface, but you can still have some force response to displacement changes. And the typical way of operating there is you set the tip oscillating, and as you move into the region where there's a force, the oscillation will change in a way that I'll point out in a minute. So what are you doing? You're driving this, so you have some drive on the cantilever so you can shake it up and down. You can shake it at the resonance frequency of the cantilever, and then the cantilever, or I call it here the amplitude of the tip, has some response. And the magnitude of that response, of course, depends on how close you are to the resonance frequency and on the quality factor of the system. And in addition to amplitude, you can also measure the phase of the response. What's the lag between when you drive it and when it moves? So how does the force then, if we have this oscillating cantilever and we're sitting here, how does that impact the oscillations? Well, what it does is it gives you a frequency shift. So it is essentially a force ends up coming in as a new spring constant in the system, you can think of it as. And so just as the spring constant overall is changed due to this new force, your resonance frequency is going to shift, and that's going to change then. If you are driving at a constant frequency, it'll change the amplitude, or if you follow the frequency, it'll change the frequency at which you're measuring. So that frequency shift is what we measure. We keep the frequency shift constant using a phase lock loop, which basically measures what the frequency is that you want to drive at to get this best phase, which gives you the maximum amplitude. And by following that phase, you follow the place of constant force. And so now we can map out constant force contours over the surface just by keeping this frequency shift constant. Another mode of driving AFM is in tapping mode. So this is sort of a mixture of these two. The non-contact mode is nice because you have no damaging interactions with the surface, but it is a weaker interaction, so it's often harder to measure the forces. Contact mode is great because it's very easy to use, and it's a huge signal, but it damages the surface. Tapping mode is sort of halfway in between. What you do is you drive the surface like a woodpecker, you drive the tip like a woodpecker into the surface, but it only very briefly makes contact with the surface, so you're hopefully not dragging and making trenches as you move across the material. So, why AFM? Well, one thing is that you can do things that you can't do with an STM, and one of those is work on insulators. Right? So STM has no hope of working on insulators, but AFM can. Here's just one example of that. These are lanthanum vanadate films grown in the Roman Engelherbert's group. And we're looking at the same material, and this image has an RMS roughness of about 1/10 of a nanometer, and this one has an RMS roughness of about 1 nanometer. And so you might ask, why is this order of magnitude change in the RMS roughness? And one thing I should have said is that these are insulating films, so we can't do STM. These are AFM measurements. Yes?
So maybe we could take a step back. We have a question online about, are we getting the same kind of information from STM and AFM? So we could just take a step back. And
sure.
Talk about
so are we getting the same information? No. So you could say, well, we're getting topography out of both of them, but the meaning of the topography is different in the two. So in an STM, the topography is a measure of a contour of constant integrated density of states. So it's a measurement of what the electrons are doing in the material. It's not really a measurement of the actual, what you might consider to be the topography of the surface if you were looking at, I don't know, how do you define on the atomic scale what that even means, but you're looking at the electrons when you're looking at an STM image. In an AFM image, you're looking at some contour of constant force, be it a contact force as you're dragging the contact AFM across the surface, or a tapping force and you're trying to measure some average force over the distance at which you're oscillating it. All of that is measuring a force. Now, what leads to the force is certainly going to be interactions between electrons in the material and electrons in the tip, but there are other, it's certainly not directly proportional to the density of states, so the topographies can be very different from an AFM and an STM. And actually, that's one of the reasons that with SNIPE, we have the ability to switch between the two, because you can actually get out different types of information from those two techniques. And as I will mention in a little bit, you know, if you functionalize the tip, for example, or if you apply a magnetic field and you do MFM, you can measure other properties of the material, not just the topography. Okay, so we have this insulator. Its roughness is different in two different images. Why? Well, this material has a structural phase transition at 139 Kelvin, and these two images are taken above and below 139 Kelvin, and that changes the material properties. So one of the nice things about having a temperature, the ability to turn temperature, is you can go through phase transitions and see how the structure changes at the atomic scale. And we can do this both on STM. But AFM is more than just a device for measuring topography. As I mentioned, you can do chemical force. You can do Kelvin probe, which is a measurement of the contact potential. You can do MFM, which is a measurement of the magnetic properties of the material. And so let me just give you sort of a brief flavor of what kinds of things you can do with these different techniques. And one other thing is you can even combine these techniques simultaneously to measure different properties simultaneously by using different modes of the AFM. I'll give an example of that as well. So here's one example. This is a silicon 7x7. So we've got silicon atoms. And measuring both topography and dissipation. So by dissipation, I mean you are driving the tip to make it shake, and that energy is going away as you move it across the surface, and it's going away because there's an interaction between the tip and the surface, which is taking the energy out of the system. And you can measure these two things simultaneously and independently. The topography will measure by doing Z feedback. If you see, you set your frequency shift, which sets your force. If you see the frequency shift one way, you pull back. If you see it shift the other way, you push in. And you do that, and as you move the tip up and down over the surface, you get this image. So this is a constant force contour, basically, of the surface. The dissipation, there you're driving the feedback. You're doing feedback on the amplitude, on the drive. So you measure what the amplitude of the response is. As you get close to the surface, maybe it stops shaking as much because it's running into the surface, or the surface is sort of dragging it down. And when you see it decrease, you start cranking up how hard you're shaking it. As you shake it harder, that means there's more dissipation. If you don't have to shake it as hard, there's less dissipation. So you record that, and that gives you a measurement of the dissipation, which tells you about the interaction between the material and the tip. You can even do this on force distance curves. So not only can you measure the force as a function of distance, you can also measure the dissipation as a function of distance and see that it really cranks in when you sort of reach to the point where you start turning around, where you start having contact, which makes total sense. If you start ramming your tip into the surface, you're going to start dissipating energy. That's one example. Here's another example. Here's a measurement of magnetic properties and topographic properties of the sample, which are taken simultaneously. This is using a slightly different technique than the one that I mentioned just a second ago. This is using dual PLL imaging. And so let me take a second to explain what that is. Actually, I'll show another picture. These are also taken simultaneously. These are bit pattern media, so there's about 200 nanometers between these dots. And all the dots have the same topographic height. These are all sort of little palladium dots, but they have different magnetic properties. Some bits are on and some bits are off. So how do you measure magnetism and topography simultaneously? Well, an AFM tip, a cantilever, has different modes. It has its lowest mode, and if you go to a higher frequency, it has another resonance mode, and it has a whole bunch of these, and they're all sort of typically in the megahertz range if you're working with typical cantilevers. And so you can drive each of those modes independently and do feedback with each of those modes independently. And so for these data sets, we measured the magnetic field in the fundamental mode. So we have this cantilever going in a fundamental lower frequency mode over a large range. And you can go over a large range for magnetic fields because the sort of length scale of the magnetic field decay is quite large. Magnetism is basically constant outside of the material. And then we measure the topography in the first harmonic, which is a higher frequency, and we do a smaller vibration of that because the topography really changes over a very short length scale. And by measuring those two things independently and just adding them to get the total drive that we're sending into the system, we can measure magnetism and topography completely independently. And so I'm giving you an example of doing MFM and doing topography, but pretty much any combination of things you can use this kind of technique. As long as the length scales on which they vary are separated from each other, and you can make independent simultaneous measurements and then look and see how they're related to each other, how they inform each other. And I think, actually, it's probably a good, oh no, what time are we ending, Kevin?
Maybe 5 more minutes.
5 more minutes? Okay, I'll give you 5 more minutes. Okay. So I'm going to end with one more technique, which is Kelvin probe microscopy. I think this is maybe not so commonly known by people, and it can give you some nice information about material systems. So here's the idea. You have a tip and you have a sample, and there's a difference in the work function of those two materials. Even when their Fermi surfaces are aligned, then you have this contact potential difference. That's CPD, contact potential difference. So how do you get at this contact potential difference? Well, the tip and the surface, they form a capacitor. There's some energy stored in the capacitor because you essentially charge it up when you put a voltage between the tip and the surface. And hence there's a force associated with changing the distance between the tip and the sample. And that force scales like v squared. And then some things about the distance, which depend on whether you're far away or close, but are irrelevant for this conversation. So if you are doing AFM, and it has a conducting tip, so you can put some voltage on it, get some charge down into the tip, and you sweep the bias of the sample relative to the tip, what you'll get for the frequency shift, that's this delta F, are these parabolas. And typically what we do is we work at the place where the parabola is at a peak, so we basically zero out any electrostatic effects, so that when we're doing force measurements, we're really looking at force and not just the electrostatic force, because you have a bunch of charge on your tip and mirror charge in the sample. But you don't have to do that. You can actually, as you scan over the surface, the contact potential is going to shift where this bias gives you a minimum frequency shift. Because the meaning of the bias, which is the potential difference between the two, changes if you have different contact potentials spatially in the material. So you can take advantage of that and do something like this. So this is CPD, or contact potential difference imaging. There's topography. They're simultaneously measured. And what they find is that the contact potential varies by about 0.2 volts over the sample. And if you look at the relationship between where it's high and where it's low, related to topography, you can see the topography definitely drives these differences. Now, why might this matter? Well, if you're making devices and you're talking about potential differences across the device, but you have inherently, due to topography, potential differences within the device, it could be larger than the potential differences that you're trying to generate with the device itself. It can be a big problem. So actually getting atomic scale information about how the potential varies across your device is a very important thing to do before you go on and try to actually use it and understand what's going on macroscopically. So with that, I will end. I hope that I've shown you today there are a wide variety of SPM techniques, and they give you powerful information about material properties at the atomic scale. Our MIP, the 2DCC, has several SPMs that are currently running, and another one which is coming online shortly. Please consider collaborating with us. We would be happy to work with you. Thanks very much for your attention.
So we have a question from North Carolina Central. They have a question of which manufacturer is the AFM system from at Penn State now.
So the AFMs that are in the MCL are from Bruker.
Bruker.
Yeah, Bruker Icons.
So I was typing in the box, those of you online, if you go to mri.psu.edu and you click on the MCL tab, the Materials Characterization Lab, you can find every instrument with all their capabilities, their manufacturer, so on and so forth, on that site when you start clicking through. So
yeah, and if you go to the AFM tab, there is a long list of properties which I did not take the time of people here showing, but they're all there.
yeah, so there's a lot of information to back that up. We have another question online. Does the surface roughness interfere with the contact potential measured in KPFM?
It absolutely can. So you need to be very careful about that as you make the measurement. You have to work at a force setting, basically, in non-contact mode, which lifts you up enough that you're not making huge variations in the height as you're doing the KPFM measurement.
So I wanted to make a note for those of you who are looking to use the 2DCC in the future. When you write proposals to use the facility, understand that the other facilities like the Materials Characterization Lab, the NanoFab, they're all available through the proposal process. The 2DCC has its own instruments, but when you want to characterize and you want to use these facilities, they can be a part of the proposal, and they can be folded into what NSF supports. So all these talks that are about these other instruments that we don't manage ourselves, you have access to them. Okay, it looks like a number of thanks from the people that asked questions. So why don't we have a question here on site while other people are typing online? Any questions here?
So Eric, I'm curious what happened in the sample that Romance
The Lantern Vanity
grown
sample?
up. Yeah,
Yeah.
yeah. So when did it get rougher?
So it's just in the process of undergoing the structural transition. I'm going to get it backwards, so help me. It's a tetragonal to...
high temperature it's orthorhombic and at low temperature it's tetragonal. So the unit cell changes and as the atoms kind of come in together, it buckles.
Yeah. And actually you see something very similar in... in another system which undergoes a metal insulator phase transition, there's a structural buckling that also increases the roughness, and there are questions of whether the metal insulator transition is driving that structural transition or vice versa, or how they interact. So being able to measure both of these as you go through the phase transition is an important capability.
We have two good questions queued up online. One is, in the case of niobium diselenide or other TMB surfaces, can you remove a Capuchin atom with the SDM tip?
Can you? Absolutely. Can you do it intentionally every time you try? No, it's challenging. It's hard. It's generally hard to knock atoms out of a lattice. If you have a step edge and you want to drag an atom to or away from a step edge, that often is a doable thing. But actually pulling it out of a single layer of the material, unless you usually when that happens is when we make a mistake and we slam the tip into the surface, and then we go back later and we see there's a hole there. But generally, that's not something that we can intentionally.
Even if you don't use the STM, you can bombard it with something else, which we can.
Sure, and so I didn't put in those images, but so for example, we're doing a study on helium bombardment of graphene, And so that's something that you can go and do that and then put it back into the STM and go and look and see what happened with the atoms that we knocked out. And we're doing that in collaboration with Tanu and John Redwing's group.
So we have one more online. So this has to do with the SPM. So they want to know, can the SPM be connected directly to the MBE and used when it's running, so in situ?
So that is the plan. Check back in a few months and see if can is yes. So there, it has been done. Joe Strosio has an MBE system. This is at NIST that's directly coupled to an STM system. It's hard because there are vibrations as you're moving around shutters and stuff in the MBE system, and that can cause problems with the SPM. So I'm not sure I'd actually want to be running them simultaneously if I was making important measurements in the STM. But certainly they will be coupled so that we can immediately take it out of the MBE and put it right into the SPM without breaking vacuum and make measurements at that point.
So just to follow up on that, the MBE system that has this in situ characterization on it, and we're currently assembling it now, we expect that it will be available for the community to write proposals to use sometime in the beginning of 2018. So it's currently being assembled. The room was refurbished. It's a state-of-the-art facility, but we are testing it now, putting it together to make sure that it is completely good for when the community wants to write proposals to use the machinery. So check back a little bit later. We keep updates on the 2DCC site in the user facility section. You'll notice in that tab currently that we have that it's coming. So it means it's not completely assembled. Any other questions on site? And I think we'll wrap up.
So if you want to tell the charge defect from the natural one, is AFM or STM better at doing that, or TEM or STM?
Repeat the question.
So if the question is, if you want to see if you have an impurity and whether it's charged or neutral, what's the best technique for doing that? That's an interesting question. So in STM, typically you can see charged impurities because they typically, if they're charged, they typically appear brighter in the topography, for example, because there's excess density of states there. And STM is easier for doing atomic scale imaging than AFM is. I didn't mention this, but it is certainly possible, as you saw, to do atomic resolution AFM, but it is not trivial. With AFM, you can actually go and measure contact potential differences, which would certainly change if you had a charged impurity. So in some sense, that's a more direct measurement than the STM one. But I think in the long run, the STM is going to be the easier way to make those measurements. Okay.
So is it at all possible to measure the density of states with the conducting AFM test?
Absolutely. Yeah, so you can do conducting tip AFM, in which case you're basically doing STM, except, and you can really do STM with the conducting tip AFM. You can go into topography with the feedback using the tunneling current and just do STM. It never works as well as a real STM. The cantilever tips tend to not be as sharp, so and the cantilever is shaking, so you tend not to get the resolution that you do in an STM. But if you're willing to sacrifice a little resolution, you absolutely can do STM with an AFM.
With that, I'd like to thank Dr. Hudson one more time for his tutorial today.